So for today's pre-lecture video, I want to take some more time to talk about the concept of energy. In chapters 4 and 5, we used the idea of forces and Newton's laws to solve problems, but as I explained as we moved into chapter 6, we're changing sort of the way we're going to approach a problem by using the idea of energy and also work, which was introduced in chapter 6. So in chapter 6, we looked at how we defined work, and we also saw that it was related to the change in kinetic energy. So we had work equals change in kinetic energy. In this chapter, we're going to introduce another type of energy, which is called potential energy. And eventually, once we understand potential energy and kinetic energy, we're going to be able to put them all together to talk about the conservation of energy. The nice thing about working with energy, remember, is that it's a scalar quantity. And so we don't have to worry so much about directions and components and things like that. We just have to worry about how big it is. And energy is going to be a way to think about a system. Remember, the system sounds complicated, but it's whatever we're looking at. It might be a box on an inclined plane or two masses on a pulley. That's what we mean by a system. But thinking about the energy of the system, we're going to be able to understand that sometimes we can have energy flow into the system, and sometimes even if the amount of energy of the system remains constant, the types of energy that we might find in the system will change as motion occurs. So that's really sort of introducing where we're going with all this. All right, so reviewing from chapter 6, we talked about the definition of work. If we have a constant amount of work, a constant force, we can define the work done as the force dotted with the displacement. In the cases where the force is a varying quantity, we have to use the integral in order to find the work done. But what we found was that if we look at the total work done, so this is net work, and these are net forces, the total work done would be equal to the change in the kinetic energy of the system. Kinetic energy is equal to 1/2 mv squared, and it's energy of motion. It's the energy that an object has because it's moving. Remember that when we learned about work, we learned that it was measured in joules, but so is kinetic energy. Of course, they'd have to have the same units, but we always think of joules as a unit of energy. And in a sense, what we're saying in this theorem is that when work is done on a system, one of the things that can change is the kinetic energy of the system. If we do a positive amount of work, we expect the kinetic energy to increase. If the work ends up being negative, we expect the kinetic energy to decrease. This is the first example of what I'm thinking of or trying to describe as energy flow, is this work kinetic energy theorem. All right, so I want to look at a situation where maybe the kinetic energy doesn't change. And so let's suppose I have a block of mass m. It's initially some initial position or initial height off the ground. And we're going to change that position to some final position. Now, we know that there's a force acting on the block which is equal to its weight. We call that mg. But if I push up with some applied force, if the magnitude of the applied force is equal to the magnitude of the weight, then actually we know from Newton's second law that there's no net force, and so there's not going to be any acceleration. But first of all, let's just see if we can understand it from the idea of work. So let's think about the work done by the applied force. So it's going to be equal to the applied force times the displacement. Now the applied force is in the positive y direction, so I'm going to write it like this, in the j hat direction. And the displacement is also in the j direction. And it's going to be y final minus y initial. So remember dot product, j dot j is just equal to 1. So the work is the applied force times the displacement. Okay, now let's look at the work done by gravity. It's equal to mg dotted with the displacement. I'm going to do the same thing that I did with the applied force. But the force of gravity is downward, so I'm going to make that minus mg times j hat. Understanding in this case that the g that I would put in would just be 9.8. I've already taken into account its downward sign with a negative sign. Oops. And the displacement's exactly the same. If we look at this, so the amount of work done by gravity is actually, if you look at it, is actually equal and opposite to the work done by the applied force because of the fact that those two forces are equal in magnitude. And that's why the change in the kinetic energy in this system would be equal to 0. Now we're going to just take a little bit more time to think about the work done by gravity and just talk about what might be happening though here. So it's same scenario. The block is going from some initial position to some final position, and gravity's acting on it. And so when we look at this, we say, okay, well, the gravity actually ended up doing a negative amount of work because of the fact that as the block moved upwards, it's actually moving opposite in the direction of the force. And so that's why the work done is negative. The angle between the two, the displacement and the force vector, would be 180. That would be another way of looking at it. But we want to think about, like, what exactly is happening when this object is moving from a lower height to a higher height. You know, we already know that the kinetic energy isn't changing, but is something else changing? And we notice that the work done is equal to these terms, a difference of terms that look exactly the same except that they have different y values. So there seems to be a quantity, mgy, that's changing when I do the work done by gravity. And what we're going to do is we're going to call mgy the potential energy due to gravity. And we're going to say that in this case, the work done by gravity is equal to minus a change in the potential, this U sub g, which is the potential energy. So this is called the potential energy due to gravity. And what we're saying is that the work done by gravity can be expressed as negative the change in the potential energy. So the reason for that is because we have U initial minus U final, is that's what we have here, which we could just write as minus U final minus U initial, which is equal to minus delta U gravity. So what we're doing is we're making a relationship between a work done by a force, in this case gravity, and the potential energy, oops, forgot my T, associated with gravity. And that's how we find a potential energy function. Basically, we're saying work done by a force is equal to minus the change in potential energy associated with that force. Gravity, we found, was equal to mgy. And because of that, we say that potential energy is an energy of position, because what happens is its value depends on where an object is. And we see this right here with the potential energy due to gravity. It depends on the position, the y position, which is how high it is above the ground. And now we can see that the potential energy of the object is actually higher at a higher location than it is at a lower location. The bigger y gets, the smaller the bigger the potential energy is. So we're going to find that there are particular potential energy functions that we're going to be familiar with. Another one that we're going to deal with is the potential energy function for a spring. And that's equal to 1/2 kx squared. So what potential energy we can also think of as stored energy. And so when the object is rising to a higher height, it's working against, the gravity is actually working against it. But what's going to happen is as it goes to a higher height, the potential energy of gravity is actually higher than it was when it was at the lower height. And so what's happening is as we move it to a higher height, we're giving it more potential energy. And it really depends on where the object is. So this is going to be helpful because we're going to also see that, so a system might have some potential energy, maybe because of gravity, maybe it's a mass on a spring, but it also could actually have kinetic energy at the same time. So and that's when we're going to start talking about the flow of energy, how potential energy and kinetic energy can transfer from one into the other, and also how work can input energy into a system, because when I do work on it, I can give it more energy. But one of the real simple things that I can think about in terms of energy flowing from one type to another is I could have an object that I have at some initial height off the ground, and let's say I drop it. Now up here it has a lot of potential energy. Here it has potential energy due to gravity equal to mg y initial, but because I dropped it, it didn't have any initial kinetic energy. As this object falls to a lower position, its gravitational potential energy is smaller than the initial gravitational potential energy, but we know that its kinetic energy is now going to be greater. And what we're seeing is, the idea is here that the potential energy that it had initially starts getting transferred into kinetic energy as the object falls. Its potential energy starts to decrease and its kinetic energy starts to increase. The total amount of energy, the sum of the two added together, will remain the same, but will go from one type of energy into another. And this is forming the basis of what we talk about when we talk about conservation of kinetic energy.